Hey everybody, welcome to a brief introduction to Swift. In this video I'll be going over the history of the Swift language and be discussing some of its general characteristics. We'll then list the reasons why Swift is a great language, followed by discussing the standout features of Swift, so the things that really make it shine. We'll then do a code demo where I'll be solving one of the exercises on the Swift track on Exercism, and we'll finish off by listing the resources that you can use to learn Swift. I'm really excited about Swift, so let's get started. Swift's development was started in 2010 by Chris Ladner, and it was announced worldwide at the WWDC event in 2014. The goal of Swift was to replace the language that was being used at that moment to build software in the Apple ecosystem, which was Objective-C. Objective-C had had some updates ever since its inception, but it was still a relatively old language, lacking some of the features that you might expect of a modern language. So that was the reason why Apple thought, well, we should replace Objective-C with a new, powerful, and modern language. And that became Swift. As there was a huge number of code bases around that were still using Objective-C, of course. One of the key design goals was that Swift would interop well with Objective-C because that would make adopting Swift a lot easier. Swift is a strong and statically typed language, and it is compiled to machine code. This compiling to machine code is actually done by LLVM. So when you compile your Swift code, Swift will compile to the representation that LLVM uses, and then LLVM, which is a separate tool, will actually handle the compiling to machine code. And there are a lot of benefits to this approach, and we'll come to that later on. This approach, by the way, is also used by other languages. For example, Rust is notable for also building on LLVM. The Swift language is a multi-paradigm language, which means that you can choose different styles of programming. For example, you can do object-oriented and imperative programming, but also declarative and functional programming. So there's a wide variety of options for you to choose from. Originally, Swift was proprietary software, so it was closed source, but it was open source soon after launching in 2015. Finally, Swift is primarily used in, well, apps, so your iPhone, your iPad apps, but also your macOS apps. But Swift is a general purpose language, so you can also use it to build backends and even to have code run in serverless scenarios. Let's look at why Swift is a great language. First of all, Swift is a very modern language. It has all the bells and whistles that you've come to expect from a modern language. And these include type inference, pattern matching, algebraic data types, tuples, Unicode strings, you name it. Swift feels very modern, and that's really pleasant to work with. And that's a huge break from Objective-C, which had its fair share of issues. A second great feature of Swift is that it's very productive. Swift is a very pragmatic language in that it adopts the best parts of other languages. It's relatively new, so there were a lot of languages that Swift could use as inspiration, and they used bits from Rust, Python, C#, and Ruby, and they took the parts that they liked best and molded that into a very productive language. So a very pragmatic and productive language, but it's still very consistent. So that's one of the best things about Swift. A third reason why Swift is great is that it is safe, especially when compared to what you would previously use, Objective-C. For example, pointers are not exposed by default. There is an optional type that prevents null pointer exceptions. Error handling is very explicit, and memory management is automatic via automatic reference counting, also known as ARC. And all these features combined makes it such that Swift is a far safer language than Objective-C, and it is basically what you come to expect of a modern language. Furthermore, Swift is updated very regularly, and I quite appreciate that the Swift designers were not afraid to backtrack on some of the decisions that they've made initially. So the first couple of versions of Swift often contained breaking changes where they removed features that they previously introduced, but found that those were not working as well as they intended. And they thought that, well, we're still a very young language. If we are to introduce any breaking changes, we might as do it right now. And I think this was absolutely the right decision, because this approach helped garbage from accumulating in the language. And it's very hard to design a language without any people actually using it. Only when people actually use it, you'll see what does and what doesn't work. And I like that Apple wasn't afraid to cut features that they found were just not that useful, even if that meant breaking things. That said, they always try to have tools available to help you migrate your code. So it wasn't entirely a big bang where they just forced those changes on you. You got some help. But in general, Apple has now reached a stage where Swift is very stable. So since Swift 5, the application binary interface, so the ABI, is stable, which means that future Swift versions will be compatible binary-wise, which wasn't the case previously. A last great feature that I'd like to mention is that Swift runs on all major platforms. So Objective-C was primarily used on the Mac platform. It could be used on other places too, but it was slightly, rather useless, and it wasn't as easy as it could be. But Swift is a modern language and it runs on all platforms. So macOS, but also Windows and Linux. And this makes the adoption of Swift a lot better than Objective-C, because you can also use it, well, on other places and for other purposes. Let's discuss Swift's standout features. First of all, Swift is fast. Swift compiles to quite efficient machine code, which makes it run fast. The fact that it compiles to machine code also means that you don't have the additional cost of translating or interpreting bytecode. So the application, once it is compiled, is ready to run. There is no hidden runtime anywhere. You just compile it. Part of the reason why Swift is fast is because it was designed to be so. It was one of the design goals of Swift, but part of it is also due to it building on top of LLVM. As I mentioned before, LLVM is the tool that handles the actual compiling to machine code, and it is a highly optimized tool with decades of experience in compiling to very efficient machine codes. It's hard to beat LLVM. A second reason why, second standard feature is that there is seamless interop with Objective-C code. As I mentioned before, previously the Apple ecosystem used Objective-C code for all their source code. So there was a ton of Objective-C code out there that was still to be maintained. And Swift was designed to interop with that really well. So this means that you could add new features in Swift while still interoping with your old code very well. So there is a very low barrier to using Objective-C code in your Swift code. Speaking of interop, Swift also interops really well with C and C++, although the C++ interop is still in beta mode, but it's almost done. So if you want to use software that was written in C or C++, Swift also has got you covered. And then the final standout feature of Swift is its large and very friendly community. There are so many excellent resources out there to learn Swift, to ask questions about Swift. It is just amazing, and it is a great community to be a part of. And I've really enjoyed the Swift community as being friendly and very fun in general. And I think it's time to start writing some Swift code. What I'll be doing is I'll be solving the Isogram exercise of the Swift track. And the Isogram exercise is one where you get passed in a string that either represents a word or a phrase, and you have to determine whether or not it's an isogram. And the definition of an isogram is a string that doesn't have a repeating letter, case insensitive. So if you have a string with two A's, it's not an isogram because it repeats. But if the string is ABC, then it is an isogram because none of the letters repeat. If you have other characters apart from letters, like numbers or hyphens or spaces, those don't count. We just look at the letters. So that is what we're going to do. I am writing this code in Visual Studio Code. partly because it's my preferred editor, but also because I wanted to show you that it is entirely possible to use Swift outside of the Apple ecosystem. You could use Xcode to write your Swift code, and many people do, but you can also write it on different platforms. So I am using Visual Studio Code on a WSL environment in a Windows 11 machine. So that goes to show that Swift is truly a cross-platform language. So let's look at one other thing that's quite important, and that is the plugin that I'm using. There is an official Swift plugin for Visual Studio Code, and it gives you lots of goodness like code completion, of course, syntax highlighting, and integration with a test explorer, etc. And it's a really well done extension. And if you're doing Swift code in Visual Studio Code, I would highly recommend you to install this extension. This file is the starting point of our implementation. We have a single Isogram function that takes one parameter named string, and its type is string2. So if we hover over the string type, we see that there is documentation. So there are a lot of examples and explanations on how the string type works. So you can see already that the integration with the Swift plugin is excellent and provides us with useful things like documentation directly within our IDE. It's all fairly normal here. The only thing that you might be unfamiliar with is what this underscore is before the name of the parameter. And that's an inheritance of the Objective-C language. So in Objective-C, your parameters can have two names. So one is the name that is being used internally in your function, and that's this name. So anytime we want to refer to this parameter, we use that by this name. And the other name, which is optional, is something that you can specify for the outside world. So if you're calling this function, you should be using that name. So right now we have an underscore, which means that the caller can just do Isogram and then pass in ABC. But if we change this to a name, so Isogram for string, then we would have to do this. So we have to supply a name value for the parameter. And this is something that is being used in Objective-C all over the place. Swift supports it too. But if you don't want that, you can use an underscore, and then it's just like a regular functional call. And that's something to be aware of. Let's start implementing this exercise. So we're going to start out with a variable called letters. This will keep track of all the letters that we've seen. So this is keeping track of every letter that we've already processed, and we can then detect whether or not a letter is a duplicate. So we're going to make this an array of characters like this. So the square bracket notation is array, and the type within the array is a character. And you can see that the compiler inferred the type for us. We didn't specify the type ourselves. The compiler did that via type inference. Then to iterate over the strings, there are a couple of options. We're going to start with a very traditional one where we're going to iterate over from 0 up to the length of the string. And then we're going to index into the string by that number. So we're going to do for I in 0 ... string count. We have to do -1 because, well, the actual count is, because we start counting at 0, we have to add the -1. But there's another option. We can also do ... less than character. And then this will have the exact same effect, because this will be up to this value instead of the 3 dots being up until, up and including the value. So this will be 0, 1, 2, up until string.count -1. Okay, so then how do we get the character? So, well, you might think character is string and then index it with I. In many languages this works, but it doesn't work in Swift. And if we hover over the error message, it says cannot subscript string with an int. Use a string.index instead. And this is because Swift is very strict with strings. Strings are Unicode, and in Unicode a single character could be multiple bytes. And that's the reason why you can't just index with a regular number, because, well, which character would it be? Would it be at byte level? So you might want the first byte, but if you want a character, it could be the first 2 bytes. So what Swift does, it has a different type specifically for indexing into strings, and that's called string.index. So let's try and create one of those. So let index, so then we'll do string.index, which is a function on the string, and we want this overload, the one where we pass in the starting index from which we offset by a number. So the starting index is just string.startIndex. So this is before the first character, basically, so the first character. And then the offset by is the thing that we actually have as a variable, so that's our I. So this line of code is giving us a string.index value, and this string.index value is something that we can use to index into the string. Right, so now we have our compiler warning going away. But you can see that working with strings in Swift is different than you might be used to in other languages. And you can also see that this named parameter thing is where what I mentioned about the underscore. The first one is an underscore, so we just pass it in, and this is a named parameter. So now we have the character. Now we're going to check if the character is a letter. So if we do dot, we get code completion, which is very helpful. So there is an is letter. We're going to reverse it. If it's not a letter, we're going to skip processing. So we're only interested in letters, so we can just skip it. So if it is a letter, then we need to check whether or not this is a new letter or a duplicate. So if letters.contains the character, that must mean that we've already seen it, so it's a duplicate. So we're going to return false. Otherwise, we're going to add it to the list. So we're going to append the character, and in the end we're going to return true. And this should be a first working implementation. So just to reiterate, we're iterating over the index. We're converting the regular integer to a string index to get the character. Then we're checking if it's not a letter, we'll just ignore it. If it is a letter, but it was one that we've already seen, we're going to return false. Otherwise, we'll return true. So let's try and run Swift test. So it says executed 14 tests with 2 failures. You might have noticed how fast it was. So we have 2 failures, and they are both tests for the case insensitivity. So we haven't done anything with casing yet. So what we actually would want to do is we're going to do let lowest string is string dot lowercase, and then we're going to use this instead of the string to have everything be in lowercase, and we're going to run it again. And with that, we have our first working implementation, which is admittedly not ideal. So we're going to do some work to make this prettier. So one obvious way to improve this is to use the fact that we can actually iterate over the characters in a string without specifying the index. So what we're going to do is we're going to, instead of having this for loop be over the count, we're going to say for character in lower string. Then we're going to get rid of this entire bit, and this should still be the same thing. So with this way of writing it, we'll just tell Swift to iterate over the string, and it will know that it will have to do all the indexing under the hood. Let's rerun it, and this passes all the tests. So we don't really need this. We can sort of inline this. So I'm going to move the string.lowercase here, rerun it, and this is our second iteration, and this is already looking much nicer. The next thing that we can do is to use guard statements. And a guard statement is like an if statement, but with a required else part, and that else part must transfer flow control. So the statements that transfer flow control are continue, break, return, and throw. So the guard is very specific in that it checks a Boolean condition, and if that doesn't hold, it will do something with control flow. So let's see how that applies to our code. This bit of code transfers flow control because there's a continue. So we can use a guard here. So instead of doing if not, we're going to do guard, and then we say else. So this is has the exact same effect as we did previously, but it's more idiomatic. Because the guard will specify to the reader, you already know that there's something with control flow, whereas with the if statement, you would have to do a bit more digging to see what actually happens. I also quite like that we don't have that little not before the character that is letter, and that we can have it as a positive thing now. So we're going to say this must be true, otherwise we'll do this. So these are guard statements. So let's see if this all still passes, and it does. We can do the same thing here. We would have to do it the other way around. So we're going to say guard that it doesn't contain, otherwise else we're going to return false. So we could have them be specified on the same line. So we can make it like this. I don't care either way. For the demo, I think I'll just put them on separate lines. So this is the third refactoring where we're going to use guard statements. For our next refactoring, we're going to look at the letters array. So currently it is an array, and an array can have duplicate values, but we know that in our case we can't have duplicate values. We just want to test whether or not a value is in that collection or not. And a much better type to use is a set. So we're going to do set of characters, and a set can't have any duplicate characters, but it has a couple of benefits over using the array. Most notably that the contains becomes very, very fast. And we need to change a little bit. We don't have append, we just have insert. And that's because it has different semantics. You insert in a set. Appending would assume that there is an order, whereas a set doesn't have any order. But this is much better collection-wise, and if we run this, it will still pass. You probably wouldn't know the performance for very small strings, but if the string would become very big, using a set would have clear performance benefits too. Whilst we're on the topics of performance, we're now lowercasing the entire string, whereas we only really have to lowercase the letters. So let's try and do the lowercasing on a individual letter basis. So we're going to remove the lowercase. This still all remains the same. We need to have a lower version of our character. So let lower char is char dot lowercase. And then let's just use that instead of our char. So, but this doesn't compile. So why is that? Well, let's see. It says cannot convert value of type string to expected argument type character. And this is once again the Unicode strings showing up, because if you lowercase a character, it is not guaranteed that you'll get one character back, because in Unicode, lowercasing a character could result in multiple characters. So it could return multiple characters, it can't just return a character, it will actually return a string. So instead of having a set of characters, we have to convert it to a set of strings. And this is again a demonstration of how working with Unicode strings can be slightly counterintuitive, because you maybe expect that lowercasing a character would just give you another character. But in this case, it gives you a string, because Unicode lowercasing could result in multiple characters. So run it again, and it passes all the tests. One interesting refactoring that we can do is to use the fact that the set insert function, so this function, returns a tuple with two values. So one is, the first value is a Boolean that indicates if the value was not already contained in the set. and the second is the new member, but we don't care about that. But so if we do insert dot, then we have an inserted, and this will only be true if the value wasn't already in there. So we can actually rewrite things a bit. So instead of having this, what we're going to do is I'm going to comment this out just for reference. So we're going to say guard letters.insert.inserted. So this will both insert the value in the set and then check the return value whether or not it was newly inserted. If it wasn't, so if the value is false, it means it was already in the set, and that's exactly what we had before. So this code is equivalent to this code. Only now with the guard we've made it explicit. So run Swift test, and again we have a nice iteration. So we're using the fact that with sets we get back a new value with the insert call, and we're using that. While our current imperative solution isn't bad, let's see what happens if we rewrite this using the functional paradigm. So we're gonna comment out the existing code for reference, and then we're gonna see what it looks like in a functional way. So we'll focus on this bit first, which is we take a string and we filter out the letters. So we use string, and there is a built-in function called filter. And the filter function takes in a single argument, and that argument is a function that takes a single character parameter and returns a Boolean. So let's get rid of that. We could define a separate function, and that would be fine, but there's also syntax in Swift to define a function in line, and in Swift that's called a closure. Other languages might refer to it as lambdas or anonymous functions, but in Swift it's a closure. And the syntax for that is that we're going to do the curly braces. Then we're going to have to list the parameters. So in this case, there's a single char character, the return type, which is Boolean. Then we'll do in, and then we're going to return our actual value. And in this case, it's char.isLetter. So what this function call does, it will handle the iterating over the individual characters within the function call. So we don't have to bother with that. We just bother with just this bit of logic. So this bit of code is the same as this. So let's assign this to a variable. We're going to call this letters, which of course we can't because we now have two letter variables, and we're going to call this scene letters instead. So this is our first step. We have extracted all the letters. Okay, the second bit that we're going to do is we're going to convert those characters, those letter characters, to their lowercase version. So we're going to do letters.map, and that's also a staple of functional programming, where you once again pass in a function, and that function can convert the input elements to a whatever type. So we are converting from a character to a string. So we're going to say letter, which is of type characters, and returns string in return letter dot lowercase. So this is converting all the elements within the letters array to their lowercase version. So these are lower letters. It's quite long, and we're going to do something about that later on. And then the final step is to transform this bit of logic into a functional version. So if you look really closely, we're basically saying that for all the letters that we found, the lowercase versions of them, the insert call must return inserted as true, because if it was to return false, that would mean it was already in the set and we would hit this bit. So we're gonna just copy this, and there's a function called allSatisfy, which is another function that takes a function. And in this case, it takes in a single element and returns a Boolean. And if any of the calls for elements return false, the return value of the function call will also be false, which is precisely our logic. So once again, we're going to do lower letter of type string, returns a Boolean in return. And then we're gonna, this must not be letters because we renamed it to scene letters. And this is lower letter. Okay, so this is a Boolean value, and we can just directly return that. So just because we have a lot of code here, let's go over it step by step. So this bit of code where we iterate over the string and we only get the letters is converted to a filter call. So we're saying string.filter and we're only returning the characters where they are a letter. The second bit is converting those letters to their lowercase version, which we do via map. And then the final thing is all satisfy, which means that for all the elements in the lower letters array, we must be able to insert it into the set without noting that it was already inserted. So let's run this, and it all still passes. So we can remove this code. We now have a very functional way of our code. Whether or not this improves the readability is up for grabs, but we're going to do some things to improve that shortly. So how can we clean this up? The first thing to note is that the way that we call these functions is very like a pipeline, where the return value of one function is the input value of the next. So this filter call returns letters, and that letters value is then the input for the map call. The return value of the map call is lower letters, which itself is then the input to the all satisfy function. So instead of having these intermediate values, we can just get rid of those and just pipe the calls to give us a very functional pipeline. And already this is looking much nicer. It should still all pass the test, and it does. But this is not everything that we can do. We can do more. Another thing is that if we just want to return a single expression, we can do this. We can omit the return because it's then implicit. And again, still passes all the tests. So this is all already improving things quite a bit. Another thing that we can do is to use something that we've already used, which is type inference. So for the scene letters variable, we never specified its type. It was the compiler that inferred it for us. And in this case, the compiler can do the same thing for all the closure types. So we have a character to a bool, but the compiler is perfectly able to figure that out himself. So we're going to remove this. We're going to remove the types of this closure, and we're going to do the same thing here. And we got rid of all the types. You can see that it's now doing string.element instead of maybe what you would expect the character, but it's an alias. They're the same thing. The only thing that has changed is that we now have the compiler figure it out for us. So functionally, it's still entirely the same. We can do two more things. One is that if this closure is the last parameter, we can remove the parentheses. So let's do that. It saves us a little bit of, probably better this way. So that saves us a little bit. And there is one other thing that we can do, which is that there is a special syntax where instead of manually defining the argument, you have special values. So this closure is a closure with just one parameter, so char. And you could also replace this bit with $0. And that's the exact same thing. The compiler will just rewrite this to what you just saw, but this is shorter syntax. So $0 is just the first argument of the closure. As the same thing applies to the other closures, we can also do that. So we're going to remove this, and we're going to use $0 here. You can see that you're not obliged to have the $0 at the beginning. It can be used anywhere. And then we're going to rerun it, and everything still passes. And to my mind, this is a lot better than what we previously had. So you can argue about the $0 because you lose the naming. But in many functional languages, it's quite common to not care as much about the names of things within these little functions. But if you care about them, definitely do use that other syntax. But if you're okay with doing it this way, then this is a very neat way to have a very short functional solution. Our final refactoring is another performance-oriented one, and it has to do with the fact that filter and map are eager calls. And eager calls means that they will be applied to every single element in the collection. And we know that from our imperative version that we had a bit of short-circuiting happening. So we iterated over all the characters, but if we found a duplicate letter, we would stop. So we wouldn't continue trying to find letters. But in this case, we are doing that. So you might remember that we had this previous version where we had letters and then we had the lower letters, etc. And this is exactly what is happening. So it will completely process them, even though later on we might already find that we don't need them. And there is a different way of working with this, and it's actually really simple to use, and it's called lazy sequences. So a lazy sequence is obviously different from an eager sequence in that the lazy sequence produces values only when needed. So you can think about this in a couple of ways, but the best way to think of it is that you have these three things in a row. So you're going to apply the filter, then apply the map, and then check this function. And if that all is valid, then you're going to process to the next element, etc., etc. So many languages have this, and in Swift it's incredibly easy to use. We're going to just do lazy dot. And with just that little change, our code is becoming incredibly better performant, especially for big collections. If this was a very big string, we would first get a very big return value, then a second big return value, and then we're going to check all the values. But with lazy, things are being processed only when they're needed, by element, and this is a lot more performant, and it still passes the test. So something to keep in mind, that by default filter and map and all the other similar functions are eager, and they will return fully materialized collections, whereas with lazy sequences you get only the value that you're currently processing, and that's a lot more optimal. And with that, we've reached the end of the implementation, and we have a nice functional implementation that is quite performant. Let's look at some of the resources that you can use to learn Swift. First of all, you can learn Swift on Exercism. The Swift track has just shy of 100 exercises with a wide variety and topics and difficulties for you to choose from. On top of that, the Swift track has a syllabus, which means that there are a lot of different exercises specifically designed to help you learn one or two concepts. So this is a great way to really get up to speed with Swift in a very nice structured way. Another document that you can use is the official Swift tour, and it's basically just that. It's a tour of the language. So once you have read this document, you'll have a good understanding of the core concepts in the Swift language. There's also a more full-featured documentation page with a full language guide and a language reference, which is more formal, but also a link to the Swift standard library. And the standard library documentation contains a description of all the built-in data types like integers and strings, and collection types like arrays and dictionaries, but also all the functions that are available to you. Then there's the Swift Playgrounds app, which you can use on either an iPad or on a Mac. And this is an app that helps you learn Swift. So you do a couple of exercises with some graphical way of showing you what the code does, and you can learn Swift in quite a fun way. So definitely try this if you have an iPad or a Mac. And then finally, there's a free Apple book developed in Swift Fundamentals that basically goes over everything that you would like to learn about Swift. So if you're a fan of reading books, this book is definitely something for you. And with that, we've reached the end of this video. I hope this introduction to Swift has been useful to you, and that we'll see you on the Swift track on Exercism. Thanks for watching. Bye.